Okay, first of all, I want to thank the organizers for inviting me. It's my first time in Taiwan. I also this morning was looking back. I gave a talk at my first QCD meets Gravity meeting, which was at UCLA in 2017, still December 13th. I don't know why, same day. And I'm very impressed by the work that has happened in the last 7 years from this community. Okay, so let's start. Everybody in the room, I'm sure, has seen already this plot that summarizes the events, published events from the LIGO and Virgo and more recently CAGRA collaboration in the last 7 years. I highlighted some of the events, the first binary neutron star, the most massive system detected so far, which lies here, the most asymmetric binary black hole, and also the only event that so far has been reported as a publication by the LIGO-Virgo collaboration from the ongoing run of 4, which was detected the 29th of May 2023. It's a neutron star black hole where the black hole lies in the so-called lower mass gap between 2 and 5 solar masses. And I also want to highlight that the number of events has almost doubled in the ongoing observing run, which has already reported 170 signal candidates, and is still ongoing and will be completed in June of next year. So in this presentation, I want to describe briefly what is the role of the waveform models in detecting and interpreting the signals. I want to highlight the importance, which has been already, quite very much discussed today and also yesterday, of the fact that we will have new runs with the current facilities in this decade and also early in the next decade, A-sharp and Virgo Next, and then new detectors on the ground and in space. And so this talk tries to address the question how scattering amplitude and word line methods can help to address the accuracy challenge, since the interferometers will be operated at much better sensitivity than today. And I wanted to, as you will see from my presentation, and also papers that came out in the last few years, the results are quite encouraging for bound orbits, waveform and scattering, using the post-Minkowskian results that have been developed in the last few years and informing the effective one-body approach with them. And I will actually discuss some papers. Sorry, something happened. I have to get used to this. Maybe I should not use this, in fact. Okay. I don't know why, actually. I'm sorry. Yeah, now there are the papers in the bottom. So this is work that I did in collaboration with the following people here in the bottom. Some of them are here, Gustav Mogul and Raj Patil. So in particular, 2 papers that have been already published, and then, but I can see them here. Okay, there is some problem. I'm sorry. The 2 are not synchronized. Sorry, I don't know what to do. Okay, sorry, maybe it just got stuck. Anyway, so let me go back. So these are based on papers that you see here highlighted, and also some recent work with the numerical relativity people in our department, in particular Harold Pfeiffer, Ollie Long, and Tony Ramos-Boades, who has left, is now at NICEF, on the scattering side. Okay, so the reason why, now let me go back to it. So the reason why we are interested in highly accurate waveforms is because the information on the properties of the binary black holes and neutron stars is imprinted in the waveforms. In particular, from the evolution of the frequency, we can infer the masses. From the amplitude and the masses, we can infer the distance to the source. From the time of arrival, the amplitude and the phase at the different detector, we can localize the event in the sky, as was very well described in the previous talk. And now this waveform is for a quasi-circular orbit binary with a spin aligned with a perpendicular to the orbital plane. But if you include the precession of the spin, if you include the fact that the orbit can be eccentric, you can have these modulations in the waveform that will provide information about spin and eccentricity. You can contrast a waveform from binary black hole to a binary neutron star, as seen in this plot on the right. And because the neutron star has a tidal deformability parameter that depends on the internal composition of the neutron star, you can have differences. And by measuring these differences, you can learn about the internal structure of the neutron star. Finally, you can compare with models that are not built with general relativity, but some alternative theory of GR, and you can probe the theory of gravity. So as has been emphasized in several talks yesterday, in particular in this morning, in order to solve this problem, we have to use different methods. So in this diagram here is represented the mass ratio in the binary, the separation, possible eccentricity. Numerical relativity is our best tool to solve this problem, but it's very time-consuming to do simulations. And so it's restricted to a certain region of the parameter space. So then we have to solve the Einstein equation in an approximate way, perturbatively, post-Newtonian, post-Minkowskian, which expand the Einstein equation in powers of G over R. So it's weak field, but resums all the expansion in velocity. And then if you have a large mass ratio in the binary, you can use gravitational self-force, which is an expansion in the mass ratio in the binary. And all these techniques are valid in some part of the parameter space shown here in the diagram. Then we can put this approach in the effective one-body formalism that also use physical answers for the merger and ring down so that it can build a semi-analytic inspired merger ring down waveform, which then can be improved with numerical relativity, as we will see. The waveform in the effective one-body approach are produced in time domain. So here you have an example contrasted with numerical relativity before calibration. LIGO, Virgo, and Cagra use also phenomenological waveform. They are built in frequency domain. They are very fast to produce. And they are built by fitting together effective one-body, post-Newtonian theory, and numerical relativity. And these two plots taken from this paper is just to show you the amplitude in frequency domain. Here is the merger of a waveform with some parameters, and the first derivative of the phase in frequency domain, just to give you an idea, the fact that they are very smooth function, and when you change the parameter, they can be fitted. And so this is another method that is used. It's fast to generate, but is less accurate than the time domain ones, just because you do more approximation to put them in closed form. Okay, in the last few years has become also quite important, also in view of the accuracy of the next generation detectors and next runs, to include also effects due to the environment. The black holes, the binary black holes, neutron star may not be just in vacuum. For example, in the case of MRIs, extreme mass ratio in spirals, the small body could be spiraling in an accretion disk around the black hole, or you can have even a binary in the accretion disk. The black hole can be moving in a gas, in a medium. And from the point of view of particle physics, it's possible actually to take into account these effects in the usual way you take into account all the effects that are there in GR by introducing some new operators that would describe, for example, environmental effects, or also, if you are in a beyond GR theory, scalar fields or vector fields, etc., that are there beyond the tensor field in GR. Okay, I have just one slide to tell you about the calibration, although I will come back to this later also in more details. So what is this calibration to numerical relativity? In the upper panel here, you have the numerical relativity waveform contrasted with an effective one-body waveform. They agree at low frequency, at large separation. They then start dephasing more and more toward merger. And then we introduce parameters like higher order post-Newtonian or post-Minkowskian parameters that are not known today, and we calibrate them to numerical relativity, reaching a very good accuracy, and then we continue this calibration until they agree very well. And then we repeat this in the full parameter space, in the parameter space, in the points where we have numerical relativity waveforms. So this is a representation of the 441 numerical relativity waveform from the SXX collaboration in the space of the mass ratio and binary effective spin. The different colors correspond to different mass ratios. And for each of these points, we repeat this calibration, and then we expand the waveform everywhere, the parameter space, expanding the fit, doing the fit. And we use then this waveform for example, the template bank. This is a projection of the match filtering template bank in the mass 1, mass 2 plane. So for neutron star black hole, a binary black hole, we need of the order of 300,000 waveforms, which include also the merger. At low masses, we only need post-Newtonian templates for binary neutron star. They don't include the mergering down because that is at very high frequency. There are also other waveforms that are used by the collaboration. I mentioned the inspired mergering down phenomenological one for inference study, another family of EOB waveform called TOB-RISAM-S. And then in the region of the parameter space where we have a numerical relativity waveform, we can interpolate them and build the so-called surrogate. They are our best waveforms, but they are limited in a certain region of the parameter space where the numerical relativity simulations are available. And also in length, they are limited by the fact that the numerical relativity simulations are only produced with a certain number of cycles because of computational, is very expensive computationally. Okay, a few words about now the future before going then into the details. So we would like to have, this is not yet actually completely, planned in the sense this is under development. New facilities on the ground, Einstein telescope in Europe and Cosmic Explorer in the US. This detector will improve the sensitivity, which can be shown as an increase in the distance at which we can see binaries. And you can see we will be able to go up to redshift where the first stars formed, which even beyond that. And in that case, if we see a binary black hole system, that could be formed because of primordial black holes and not the black hole that formed with stars, because of the collapse of stars. This detector will be more sensitive also at lower frequency, which allows to see black holes much massive that we see today. Today, the maximum mass that we have seen is around 100 solar masses. We could see even thousands of binary black holes. The number of events will be very large, with SNR larger than 100, which is a factor 10 more than what we can see today. We will have of the order of 10,000 binary black holes and 400 binary neutron stars, which is really very important to do exquisite test of general relativity, but also understand the equational state of neutron stars. At the beginning of this year, LISA has been adopted as a mission by ESA with large participation also from NASA. Adopted means it's started to be built. It will be launched in 2035, and it's a beautiful mission that will allow to see complementary sources with respect to the detectors on the ground. This is the noise spectral density of LISA. You see peaked around the millihertz. And here you see some tract of the events, the massive binary black holes of 10 million solar masses sweeping in band, the white dwarf in our galaxies. We will have sources like stellar origin black hole that we see today with LIGO and Virgo starting to sweep in band in LISA, and after a few months or even a year be seen on the ground. And these tracks here are the harmonics of the extreme mass ratio in spiral signals. The signal will be much louder than today. They last for weeks, months. In fact, they will be there all the time, and they will be much more complicated than data analysis. So let me now introduce this accuracy challenge, and I have two examples to tell you that we cannot use the waveform that we have today. Otherwise, we are going to have problems. So the first one, this makes a link to the previous talk by Xin-Yu, concern cosmology. So let's consider a binary black hole with mass ratio around 6, highly precessing, at a distance 240 megaparsec, which is where we have seen, for example, the most asymmetric system with the previous run of LIGO and Virgo. The signal-to-noise ratio of that system for the next run will be around 100. A sharp, the upgrade of LIGO at the beginning of next decade, will be 200, and the next generation detectors on the ground more than 2,000. So we learned in the previous talk that we can measure the Hubble-Lemaitre parameter if we get the distance, and also for dark siren if we can localize the galaxy close to the event. So what we did in this study is to use the two state-of-the-art waveform model from the IMR phenom waveform family and SEOBNR. We use one of them as the signal, and we recover the signal with the template from the other family. The true value is here for the distance, and you can see at this high SNR, the posterior distribution does not encompass the true value at 90%, even for the next run of 5. And in this plot, you see the localization in the sky. Here is the galaxy where the event was, and the posterior distribution do not encompass this value, the galaxy. So this will create a systematics and will lead to a wrong Hubble-Lemaitre parameter measurement, which is actually not very good if we want to shed light on the current tension on the Hubble-Lemaitre parameter. The other example I want to make is about black hole spectroscopy. We heard about yesterday from Vitor talk. So I'm considering here a massive black holes of a million solar masses detected by LISA with a signal-to-noise ratio around 200. And here, a numerical relativity waveform is injected in the data and is recovered with a state-of-the-art SEOBNR waveform, where the ring down frequency and decay time are augmented by a coefficient. So there is a deviation from GR. And because the injection was general relativity, was a numerical relativity waveform in GR, we should find the posterior distribution that encompasses the GR value 0. But we don't find that. We found actually a false deviation from GR due to the fact that there is a systematics in the waveform. And so this leads, would lead actually to, as I said, a claim that general relativity is violated, while in fact this is the problem of the modeling. Okay, so there have been several papers that pointed out in the last few years that in fact we have to improve the waveform by 2 orders of magnitude, more or less, even more in some part of the parameter space. But since we calibrate the waveform to numerical relativity, we have also to improve the numerical relativity waveforms. In particular, not just for binary black holes, which is the main topic in this talk, but also for binary neutron star black hole, for which the numerical relativity waveforms today are not actually very accurate. And we have to include all physical effects in the waveform to avoid the systematics I was talking about before. So, for example, today, the main waveform model adopted by the LIGO-Virgo collaboration are for quasi-circular orbit. We need to include eccentricity. Memory effects are not actually there in many of the waveforms used by the collaboration. Astrophysical environmental effects, I was mentioning at the beginning the fact that the binary could be in an accretion disk. There could be, for example, even a third body that has an impact on the binary, and this imprints also on the waveforms. There could be gravitational lensing effects. You could have a binary that emits gravitational waves before arriving to the detector LISA. It could encounter a lens. Depending on the mass of the lens, you have a distortion in the waveform. The waveform unlensed is black in this figure here. The one in color is lensed. The lensing can also produce multiple signals corresponding to the multiple images that you would have if you have an electromagnetic signal that is lensed. in electromagnetic astronomy. Okay, so to achieve this improvement in accuracy, we have to, first of all, push the perturbative calculation at higher orders, then combine them in the effective one-body approach more effectively than we do today, perhaps even developing some novel ways of resumming them. We also need to improve our calibration to numerical relativity. Today, the state-of-the-art waveform, whether they are phenomenological or effective one-body, they are not at the level of the error of the numerical relativity waveforms. And of course, in the last few years, there has been a lot of work in this community of providing new tools to solve the two-body problem in classical gravity. And we hope that this particular post-Minkowskian calculation can help in the eccentric problem. So I was mentioning before, the new frontier in modeling is eccentricity. What you see here is a visualization, is the flux actually emitted by two black holes going around each other. The waveform is illustrated in the bottom. The eccentricity at the beginning of the run is around 0.6, but then is washed away during the evolution. And the spins of one of the two black holes were not zero, and this was producing actually the orbital plane to precess. So this plot has been shown also before, is just emphasizing the fact that because in post-Minkowskian one is actually not expanding in the velocity, one would expect an improvement for eccentric waveform. Well, this has to be proved, okay? So we don't know, actually. This is more an expectation. Okay, so now let me go to the main part of my talk, going a little bit more in details, how until now we have actually included the PM results. So let me start with how the PN results are included in the EOB approach, because this is what has been done until recently, and the waveform used by the LIGO-MIGO collaboration used the post-Newtonian results. So the effective one-body approach maps the two-body dynamics in the one-body one, where you have an effective body that moves in the geometry of a deformed Schwarzschild or Kerr black hole, where the deformation is represented by the parameter nu. So the approach provides a mapping between the Hamiltonian in the effective description and in the real description, which is given by this formula here. Now, if we go non-spinning, the effective Hamiltonian is very simple. It's just a very simple deformation of Schwarzschild. So this is the Hamiltonian of a body mu moving in Schwarzschild if you were putting this potential to zero. And for the Sion potential here, A, if you put all the correction that depend on nu to zero, this is just Schwarzschild Hamiltonian for a test body that moves around the geometry of Schwarzschild. And these are the post-Newtonian correction at 2pn, at 3pn, 4pn. The 5pn are not known. By the way, whatever is in Sion in the next slide is what we calibrate to numerical relativity. So the 5pn, we need one coefficient, which is not known today, which is the second order GSF term. And so we need to calibrate the 5pn to numerical relativity. We also do resummation of the potentials. This is an example using a Padesi summation of the potential A divided by R squared. It's a function of R. In Schwarzschild, this quantity has a peak at the light ring. Changing the mass ratio, you can see how smoothly this potential changes. So now let's go to the spin. So the deformation with the inclusion of the spin effects was done in this form originally. In this was constructed actually for the post-Newtonian approximation. But in the recent paper with the two Gustavs, we have actually used the same ansatz. So now the new Hamiltonian has the gyro magnetic coefficients here. There is still this structure here of with the potential A. And the correction that now depend on nu are going to enter this coefficient here and also the gyro magnetic coefficients. By the way, U is just M divided by R. And my notation for the spin are just displayed here. So the potential, if we put nu to 0, we recover just Kerr. So this is a deformation of Kerr, and the potential B of Kerr are not changed. So here you have an arbitrariness. I mean, you can decide what do you deform, and we included the deformation in A and the gyro. Now, in the last few years, there have been all this development in PM. So this table represents the results, zero spin, linear spin, quadratic spin, etc. And these are all the papers that have been written. And I still have this one. So at 4 p.m., as you know, the results for bound orbit are not complete because of the tail effects that we still don't know how to go from the unbound case to the bound case. At 5 p.m., we had recent results at linear order in the spin, but of course it's not yet completed. Now, in the future, when I refer to 4 p.m. or 5 p.m., I mean actually this diagonal here. Is the power in G, okay? So how we add this deformation, as I said, in the potential A and in the gyro. In particular, the evening spin PM corrections through 5 p.m. are here. Through 5 p.m. the odd spin correction enter in the gyro here. And then, because at 4 p.m. we don't have these tail effects that because of the problem going from unbound to bound, we complete we add the 4 p.m. corrections such that we can have the tail effect at least in post-Newtonian order. Now, how do we actually do this mapping? How do we compute these new terms, delta A and delta G? Well, this is using the information from the scattering angles in PM. So from this Hamiltonian, you can basically compute PR. Okay, you just invert this relation here. And then once you know PR, from this formula, you get the scattering angle in the effective one-body description. And then you just map it to the post-Minkowskian results. And you can fix all the coefficients. So this correction in delta A and delta G appear as an expansion in the spins with the coefficients here that depends on nu, the deformation, and on gamma, which is just the effective divided by mu. And then the gamma is actually re-expanded, gamma, the Kerr case, plus corrections that depends on the symmetric mass ratio. Okay, so now we have a new Hamiltonian, which is not based on Pn, is based on Pm plus these 4 Pn corrections that I mentioned before. We can evolve the Hamilton equations, which I wrote here, with the radiation reaction force. So we are not including post-Minkowskian results in the radiation reaction force, not yet. So we use just the expression from post-Newtonian theory and also actually second-order gravitational self-force, which are available in the non-spinning case. We use our code Python SEO-BNR, which was developed in the last few years to produce waveform much more accurate, much more fastly for LIGO, Virgo, and Kagra applications. So this is an example of the dynamics of the trajectory that you see on the left for a certain value of the parameters. This is the orbital frequency. It increases over time. It reaches a peak close to the light ring. I'm not yet going to the mergering down, just look at the in-spiral. And here we could compare, just for the in-spiral, how this model compare with numerical relativity, the binding energy. We can extract the binding energy from numerical relativity, and this is shown in this plot as a dashed line. And this is compared for different mass ratio as a function of V, or as a function of the number of gravitational wave cycles to merge, with 3 curves here. SEOB PM circular orbits. You can see they start deviating before reaching merger, assuming just circular orbit with no dissipation due to gravitational waves. Not surprisingly, they start at some point to deviate. If you add dissipative effects, you have the continuous line, and you can see the very good agreement with numerical relativity. This is the fractional difference, 2% below 1 gravitational wave cycles before merger. And the SEO-BNR V5 model is the model used that we developed to be used by, currently used by the LIGO Virgo Kaga collaboration, which has the 5 PN post-Newtonian term calibrated to numerical relativity. So without any calibration to numerical relativity, just using plain PM, but in the EOB formalism, we can achieve very good agreement comparable to the model calibrated using post-Newtonian results. This is non-spinning. On the left, you have now the results for the spin orbit contribution to the binding energy. And here you see 2 p.m., 3 p.m., 4 p.m., 5 p.m. And the 5 p.m. is within the numerical error, which is in gray. And compare with the model V5, calibrated to numerical relativity for the non-spinning term A6 and the spin orbit term DSO, which is also very good, but is calibrated. What about the spin-spin? This is actually another example, extracting the binding energy for the spin square term and comparing with the post-Minkowskian results and also with V5, again calibrated to numerical relativity. So this is very encouraging. But let's move forward. We wanted to get the entire waveform, including the mergering down. So what do we have to do? Okay, so we have an expression for the in-spiral plunge strain waveform, which was mentioned yesterday. We used this resummation, which was originally introduced in this paper by Thibaut Damour in 2009 and then extended to spin effects in the other papers, where the post-Newtonian results are factorized in a certain form. And also we include the results from gravitational self-force. The Sion is a calibration. So then what we do, we have actually the evolution of the waveform. We have the increase of the gravitational wave frequency and also the orbital frequency. You see twice the orbital frequency. This is the least damp quasi-normal mode. We have to do the transition to have the full waveform merging down. And in the EOB approach, what we do is that we basically build the merging down using a function that depends on time that multiplies the quasi-normal mode. This function that depends on time allows to do this basically transition here. I show you again this. So here is without merging down. This is with merging down. Now, there is a parameter here which is called delta TNR. It's just that at some point you have to decide where you have the peak of your waveform starting from low frequency, and you want to have this peak align where the numerical relativity peak is. And so we use a calibration parameter to make sure that the peak of the EOB coincide with the peak of NR. So this is delta TNR. Okay, so the full waveform is going to be the spiral plunge plus the merging down after this peak of the, in particular here, the Tutu mode, but this is repeated for all the modes. So let me show you now the performance of the PM model. So in order to show you how well the model perform, we have to compare with numerical relativity, and we compute the mismatch, which is basically a quantity. If it is very small, means numerical relativity is matched basically perfectly. It's just built by taking the overlap between the numerical relativity and the model divided by the noise spectral density of the detector. You normalize the H and G and you get this expression here. Then you maximize on the time and phase at coalescence. 1 minus this is the mismatch. So let me show you the results. Again, the 441 numerical relativity waveform from the SXX collaboration, tuning only this parameter, which is the merger time, nothing else. We are not adding new parameters in the post-Minkowskian Hamiltonian. So this plot shows the fraction of cases which have a mismatch smaller than a certain value. And this is the maximum mismatch, means we basically compute the maximum value, changing the mass of the binary between 20 and 300 solar masses. The takeaway of this plot is that the post-Minkowskian has this median here, which is smaller than the model that uses only post-Newtonian. And the only difference between these two models and the very good model in green is that the very good model in green was calibrated in the Hamiltonian against numerical relativity. But otherwise, again, this in some sense is a confirmation of the good agreement during the in-spiral against the binding energy. The post-Minkowskian result is better than PN. in recovering the numerical relativity waveforms. So I have another plot to show you these results, which now shows the maximum mismatch as a function of the spins. And I want you to focus on this part of the plot that shows where actually the mismatch is worst. It's worst for large spins, in particular for PN, but also for the post-Minkowskian model. And so this gives, encourage people to actually increase, push post-Minkowskian calculation with spin effects, but also maybe we should resum these spin effects. Is not just enough to have them in the post-Minkowskian, expanded form. So I have another plot to show you again this improvement with respect to post-Newtonian. This is again the mismatch as a function now of the mass in the binary. And this is for the model that use only PN, post-Newtonian, and calibrate only this delta T and R. And this is what you obtain if you use post-Minkowskian. You see that the curves go down and now are at the level of 10% without still any calibration to numerical relativity. And just in full glory, I want to show you one waveform. This is the comparison of the model built with a post-Minkowskian Hamiltonian against the numerical relativity for a certain value of the parameters here. Okay, so now I want to say a few words about the fact that in the last year, we have developed the first non-precessing spin, sorry, it's not the first, it's the second actually, but it's more accurate for eccentricity with eccentricity and non-precessing spins. And this work was led by graduate student Aldo Gamboa. I can show you some waveform here compared to numerical relativity on the left for the different harmonics. So very good agreement with an R. We also validated the model against the numerical relativity waveform that were developed, produced with the SXS code. They are represented in this parameter space of eccentricity and mass ratio. And you see the agreement is less than 1% for eccentricity up to 0.5. Okay, now the equation, there have been also a lot of work in the literature, including also this effective one-body model called EOB resum as DALI, and also numerical relativity simulation with eccentricity also. So the question is that we would like to tackle in the next year is, okay, now we have an example where we can include post-Minkowskian in the eccentric case and really address this expectation that we think post-Minkowskian can do better. So I already showed you that in the quasi-circular orbit case, this can be better, but maybe with eccentricity, it's even better. Okay, how much time I have? Because I had also a problem at the beginning. 5 minutes? Okay. Okay, let me finish then with a discussion about the scattering. I think I'm okay. So now I'm going to discuss the comparison of models, effective one-body with the post-Minkowskian information with numerical relativity. And so these models, the main models I'm going to show you, which are this WPM, which was developed in this paper by Damour and Retegno, and then our recent work with the two Gustav, sorry. So here it's a bit different. So the scattering angle from the EOB uses, for example, the Hamiltonian, where the dissipative effects are included directly in the Hamiltonian, together with the conservative ones. So this is a plot that shows the agreement for a certain value of the energy of the scattering angle with numerical relativity. This is the fractional difference. So you can see the agreement is quite good. Now, this is at 4 p.m. If you want to compare with the spinning results for the scattering, here the numerical relativity simulations are obtained with the Einstein toolkit code, by the way. This plot is the energy at a certain energy as a function of the spins. You can see that if you were adding the spin effects up to 5 p.m., but the non-spinning are not known at that order, you see more disagreement between the models and the numerical relativity results. In one case going to 10%, in the other case is even 50%. So this again, encourage to complete the results at 5 p.m. non-spinning. So the new results are now here. So as I said at the beginning, Oliver Long and Harold Pfeiffer have been producing for the first time results using the spectral Einstein code of the SXH collaboration for scattering. And these are very precise results. As you can see here, the scattering angle, for example, for the value of gamma that I was showing you before as a function of the angular momentum. And this is the fractional difference in the scattering angle with the models. Here also, SUB NRV5 was added, which also agrees quite well. The errors of the numerical results are incredibly small. You don't see them actually here. And in fact, if you zoom here and you contrast these errors with the one of the Einstein toolkit, you can see the difference in the errors. So Ollie produced also an event which is really amazing. It's a capture. So it's not a scattering. After the first encounter, the two black holes go around each other, do a couple of cycles, and then they merge with each other. And this is the waveform that comes from the simulation that we would like to reproduce with the models. So this is the waveform in the first encounter. And then in the second encounter, there are a few cycles, and then they ring down. And you see also even the memory effect here in place, since it doesn't go to 0. Okay, continuing on these results on the scattering, now fixing the angular momentum and changing the energy. These are new results with the spec code, contrasting again the models with the numerical results, and you see good agreement between with the W model and the SUB PM. And in this other example, the energy is fixed, the angular momentum is also fixed, and one is changing the spins, and the two spins are aligned with each other. And again, the agreement is up to maybe 12% for one model and 3% for the other. This is also another interesting result. If you assume that the spins are not equal, so one is up and the other is down, for example, then each of the black holes will have a different scattering angle, and the code is so precise to actually measure these scattering angles that you see here in the upper panel of the plot. And so this is actually the error, the difference actually between the scattering angle of the two black holes. And even in this example, you can compare with the models. For the models, the angle is computed taking the average of the two values. Now, here are the numerical relativity results. Here are the models. But if you look at the scale, I mean, the difference is still of the order up to 5%. But again, look at the errors in the numerical relativity simulation. They are incredibly small. So it will be difficult to achieve that. Finally, a paper appeared just a few weeks ago from the people in Birmingham, where they did some new simulations of scattering using the Einstein toolkit at larger and larger energy. And this simulation go to smaller and smaller values of the impact parameter. So gamma is increasing, and the center of mass velocity, as you can see here, is increasing. And now I want to show you the results. There are many cards here. These are the post-Minkowskian vanilla result in dashed, and SUB PM at different post-Minkowskian orders. I would like you to just concentrate on the green and the blue. So for this value of the energy, the 4 PM is really on top of the numerical, okay? Then you increase the energy. You see that there is now the 3 PM is here, the 4 PM is here. You increase the energy, still bracketing the numerical result, but not on top of it. Doing like this, then like this. And then finally, the two cards move on the right, and actually they, in particular now the 3 PM becomes closer to the NR, and the 4 PM is here, okay? So this means the models are becoming less accurate as you go to large energies. I mean, this is not surprising because you are also going to more in the strong field, but maybe it's hinting, so something else that is happening in the models that needs to be understood. Finally, my last slide. So let me summarize. So to address the accuracy challenge, the perturbative calculation should be pushed at higher orders, and combine the effective one-body approach more effectively, and maybe also in novel ways, to achieve this improvement of a few order of magnitude that we need. So we built the first inspired merger ring-down EOB waveform model for aligned and anti-aligned spin black holes. They use the PM information that is available today. The rest, radiation reaction force, gravitational modes, it's all post-Newtonian, in some places also GSF, okay? So I show you the very good agreement of the binding energy without doing anything, just basically including the post-Minkowskian without any calibration to numerical relativity. When calibrating only the time to merger, the model with post-Minkowskian information performed better than the model that just used PM. By the way, I also want to emphasize it's not just PM. There is always that 4 PM corrections to be completely clear. So we have now the first simulation produced with XXX for two-body scattering, which are very, very precise. The two models agree within a few percent at low energy, and there is at high energy this strong dependence on the PM order that is used. So what we want to do is to try to resum the potential. So we want to calibrate now the PM, SUB PM to numerical relativity, which we have not done until now. Include also the PM results in the EOB radiation reaction force and gravitational modes, especially if they will be available at higher orders. Extend to eccentricity to really trying to see if it is really true that PM is going to, give us a gap a lift in accuracy. And also, as new PM results become available, we will be very happy to include them in the effective one-body approach. And finally, I want to thank also the entire department, because a lot of work I showed also depend on many other people than with respect to the one I just showed you at the beginning of my talk. And thank you for your attention.
Yes, thank you very much. Time for some questions. Oh, thank you for the excellent talk. I have actually 2 questions. The first is, you're showing faithfulness by keeping, of course, all the physical parameters fixed. How do you know if we might be misled into thinking, the binary has the wrong mass or spin when we do a search with these templates?
Yeah. So for the search, in fact, as you say, we don't actually. So the search is not used to identify the parameters of the binary, so we can actually allow the parameter to change. And I think this will not be a problem for a search. We are interested in the parameter estimation part of the data analysis, where we infer the properties. And that's why we do these plots without changing the parameters, because if we were changing the parameters, then we will have a systematics, basically.
But I guess my question is, then why do we need all of this? If we can't we have an event? Why don't we go to NR instead?
To NR?
Yeah.
No, we cannot use, NR, so the only thing we can use based on NR are the surrogates. But the surrogates are not available in all the parameter space. The surrogates are available also with a certain length. So it means you can use them only for a total mass larger than 60 solar masses. So if the binary had mass smaller than 60, they are not long enough to do parameter estimation with it. They are not available with eccentricity. They are not available with spin precession in all the parameter space. So that's why we cannot just use numerical relativity.
And a very last question.
Yeah.
When will we stop then? What's your estimate
for when?
Yeah,
in fact, thank you for the question, because I forgot when I raised this point, because I really wanted to tell you. Okay, so you see now this, you say, okay, we are okay. No, we are not okay. This is 10%. Okay. For a line spin, the best model we have today, which is SUB NR-V5, calibrated to NR, is at the level of 10 to the minus 3. 10 to the minus 3 in this plot. When we say we have to improve to orders of magnitude, we have to go to 10 to the minus 5. Okay? So when we say we need waveform accurate, better than today by 2 orders of magnitude means that in this plot, for aligned spins, we have to go to 10 to the minus 5. And we are at 10 to the minus 1 without doing any calibration with the PM. I'm telling you that if you do the calibration with numerical relativity, in the case of post-Newtonian, you arrive to 10 to the minus 3. I don't have a plot to show you that, but that is the current model. But then 2 orders of magnitude, you have to go up to the 10 to the minus 5. Okay? Cioè, this gives you a sense of how much we have to improve. And this is only a line spin. Yes?
About this high energy test of these models, we actually know that PM breaks down at high energies because, for instance, these tails depend on the energy flux. And we know that the total energy flux for high enough values of the energy, it actually exceeds the incoming energy if you just take the PM answer. So I think we know that something's going on at high energies in PM because PM perturbation theory breaks down.
Okay, maybe we should talk about this because I was discussing with Gustav that, and I don't know if this is the same thing, but so yeah, and also Radu this morning had a slide about that. You know, there is at 3 p.m. everything is finite, but at 4 p.m. there is the log, and basically when you go to high energy, there is a divergence.
Yeah.
So it could be that the problem, but then how do we fix the problem?
Well, we need to find what pieces we're missing of the answer, which PM by itself doesn't capture.
So
I mean, it's not
then
clear.
you are saying the 4 p.m. is incomplete, not just because of this problem of the tails going to unbound to bound, or is this the problem?
Well, I think there's the tails going to bound, but even if you captured those tails correctly, I think still PM perturbation theory could break down for high enough energies.
Okay.
And we cannot trust any PM answer.
Okay. That will be very, very interesting to improve because we do see this problem.
Even the fluxes at 3 p.m. we know have this issue. You don't even need to go to 4 p.m., but if you look at the 3 p.m. fluxes from PM, they also have the same issue.
Okay, okay, that I didn't. Okay.
In fact, I just wanted to ask, how do you deal with the tails in here?
So at 4 p.m. is just that we are adding all that we know from post-Newtonian at 4 p.m. So we take the results of 4 p.m., okay, whatever is known, but then we complete them for the tails part, adding the 4 p.m. terms that are there at 4 p.m. order. Sorry, there is all PM here is always very confusing. Sorry. Okay, I don't know if I answer your question. We just are using the post-Newtonian.
Okay, so in this range, the tail effects, you can only do it with in the post-Newtonian.
Yes.
Exactly.
Yeah, for the moment, because we don't know how to fix them in PM.
Okay, any final question? Mattia, you can ask her afterwards.
You ask the question?
He's my student, so he can ask you afterwards.
No, but come on, this is...
Okay.
No, okay. No, I mean, two quick things. The first thing is I was wondering about all this waveform modeling and this Hamiltonian approach. How can you extend this in the case of in the presence of an environment, such as, for example, a cloud surrounding the black hole or just the merger inside some other kind of medium? And the second thing has to do with, you said that you do not have a calibration with numerical relativity. I see that delta T and R parameter in there. Is it possible in the future to get some result that is completely NR independent?
Okay. So let me answer first the second question. You know, the delta T and R, it will be great if one day someone gives me really a prediction from perturbative result, we put it in the model and it predicts even exactly where is the peak of the merger. Because this is the problem, right? You start at low frequency and then you have to have a peak and then, okay, from that point on you have the rebound. But you have to predict the amplitude and in time, the time to merger has to be predicted exactly. Until now, we never had this. So if in the future, one as a way of, I don't believe that this will come just from naively adding post-Minkowskian or post-Newtonian order, because it's really in the strong field. So maybe you have to do something which until now has not been done, and we don't know how to do, okay? Now, the other thing that you said about the environmental effects, yes, this is possible. For example, people have investigated for emery, if they are moving in an accretion disk, the effect of having, basically you have like a torque due to the accretion disk, to the gas on the small body, and you can show that this effect is a -4 post-Newtonian effect, -4 PM, which actually is there at low frequency, contributes quite a lot at low frequency. So yeah, there are ways in which you can include this effect, like a force, that basically acts on the body. And in the work that maybe also you have done with, I don't know, Daniel, or Daniel has done with other people, this is also a contribution to the force, a contribution to the flux. Then you just put in the equations of motion that I was showing you before, that you basically put in this equation, because the force depends on the flux at infinity. So yeah, there are ways of including the environmental effects.
All right. Thank you very much. Let's thank Alessandra again for a nice talk.